All right, let's see. Welcome everyone to today Rubin Science Assembly. My name is Andres Plazas Malagon. I work for Slack National Accelerator Laboratory and I'm part of the Rubin Community Science team. And today we're going to talk about how to analyze the LSST point spread function or PSF. Our agenda for today, we're going to start with announcements as usual. And then the bulk of the session will focus on going through two tutorials from the DP 0.2 simulations. These are tutorials 12A, the PSF data products. It's an introduction to the PSF. And then there's going to be a second tutorial. It should be 12B here. There's a typo there. But it's a science demo focused on weak gravitational lensing. As usual, this is the GitHub repository where you can find these tutorials. The announcements, we're going to have our Rubin 2024 community workshop in July, the 22nd to the 26th at Slack. There's going to be a virtual component as well. You can still contribute with your talks and posters, abstracts, so that's still open. So please check this community post that is highlighted here. The registration is open as well. Keep in mind that there is a limit on the number of people and a deadline. And in addition, there is a call for grants from the LSST Discovery Alliance in case you need financial support for childcare in order to attend this meeting. So please follow this link as well in order to take advantage of that opportunity. We're going to have also our Rubin Data Academy in 2024 in June 17, 21. 21st. So this used to be called the DB0 Virtual Summer School last year. This year is called the Rubin Data Academy. And this is a virtual intensive series of presentations and hands-on tutorials and co-working sessions. Students are especially welcome and everybody with any level of background is welcome as well. So no experience or preparation needed. So the registration is open, and so please follow the link that it's available in these slides. We also wanted to announce that we have now some DP0 tutorials that have been translated into Spanish. So that's great. So that's a contribution led by some members of the Argentinian in-kind contribution team. So please check those out and spread the word. I also wanted to highlight the LSST, the first LSST at Latin America meeting that is going to take place in La Serena, Chile, from June 10 to 14th. And we're going to have also the LSST at Europe 6 in September, 16 to 20th, in La Palma, Spain. So that sounds very nice. But La Serena is also very nice. So check that out. If you haven't checked this out, go ahead right away if you want to. There is a very nice video of the coding of the mirror, the primary and tertiary mirror of the LSST of the Rubin Observatory of the Simoni telescope, along with a press release. It also has versions in Spanish as well. So check that out. This is pretty cool and mesmerizing as well. Finally, just a reminder, we have a schedule, a calendar for resources on DP0 and a calendar for the assemblies, and also in this website you can find any resources for DP0. We don't have next week at this time, we don't have an assembly, but of course you're always welcome to ask any questions in community. Keep doing that. I know many of you already do, so that's great. And 2 weeks from now, we're going to have a tutorial by a session led from a tutorial by Christina Williams, another member of our community science team, on how to use the image cutout service. Those are the announcements that I have. Just going to pause a second in case anybody has any more announcements while I change here and start. If we don't have any announcements, we can go ahead. So if you have any questions, feel free to interrupt me or write in the chat. It's going to be a little bit hard for me to check the chat. So hopefully my colleagues or somebody can interrupt me and I'll be more than happy to answer your questions. So we're gonna start. So we're gonna cover two tutorials. It might be a little bit too much. We'll see. But they're both tutorials that are related to the point spread function in the LSST. Especially, we're of course using the DP0.2 simulations. And so this first tutorial, as we can see here in this table of contents, we're going to retrieve the single epoch and the co-added images. We have single epoch and co-added images in the DP0.2 simulation. And then we're going to see how those objects have the information of the PSF model, what we call the PSF information, among other types of information that useful that we can get. We're going to learn how to display this PSF model. And then we're gonna have we're gonna do this very simple plots on how to first order analyze these images or these models that we're getting. For example, making radial profile plots or two-dimensional contour plots or curves of growth. So this is gonna be the first tutorial in the first half hour of our assembly. So yeah, so maybe some of you have already checked this tutorial as well, but I just wanted to point out, of course, that I led the development of this, but I had the help of many of my colleagues from the community science team. So I wanted to acknowledge that as well. So basically, the point spread function, to start, we can understand what is the point spread function in simple terms as how the light from an astronomical point source, or in general any point source, is spread out in an image. So that's basically it. In astronomy, stars are so far away that they're basically point sources. And if we had a perfect detector, whatever that means, we would see a point source in our detector, but we don't see that. We'd see a little blob, or we see something. We see how the light from that point source spreads, and that's the kind of thing that we want to analyze. In particular, my background is in weak lensing, in which we want to learn the distortions, the subtle distortions of galaxies of the large, caused by the dark matter of the large scale structure. And in order to learn that distortion that has information on dark energy, dark matter, we need to take into account this point spread function that is kind of contaminating, so to speak, this image, or is convolving the signal that we're after. So it is very important to analyze, to measure, and to model as accurately as possible this point spread function. In the LSST science pipelines, in a very high overview, the initial stage of imaging processing starts with something that is called instrument signature removal. And actually, this is something that I work on in one of my other teams in Rubin, so I'll be happy to answer questions about that. But this basically encompasses what we call the trending and operations, like doing flat fielding, bias subtraction, and dark subtraction, and something like that. But then after this, we start characterizing single epoch images, and that entails all the conversion of how do we convert the image that we have in our detector into a representation of what of the sky, of the image of the sky. And in this process, we do things like background subtraction, and then part of this is this point spread function modeling. But just wanted to put that in context. And in the way in which we do the PSF measurement is the way that we sample and we actually measure this PSF. The PSF it can be thought as a two-dimensional function. You can go from a delta function, which is your point source, into a two-dimensional function in your pixel coordinates, X and Y. And you sample that at the locations of the stars. And usually you measure bright stars because they have higher signal to noise, and that tells you about the information of the PSF. But then right away, you can start thinking that I'm interested in the PSF in another point, like where the galaxies are. So there's going to be some sort of interpolation. And then other questions that we need to think about is if we're doing an analysis in co-added images, for example, how are we going to co-add that PSF model into a final coordinate image. So these are the kind of questions and that are very challenging and going to PSF modeling in this type of galaxy surveys like the one that the LSST is going to do. So the LSST science pipelines recently have transitioned into using PSF modeling code that is called PIF. PSF in the full field of view is used by a precursor survey called the Dark Energy Survey. But the models of the PSF that were generated in DP0.2 were generated using the PSF extractor software written by the same person who wrote Source Extractor. So there are differences and there are subtleties, but in the LSST science pipelines, we're using, right now we're using a combination of the two, but we're also transitioning to use PIF. So moving on into the notebook. So maybe I might go a little bit fast, but I'll be happy to answer questions if there's something that is not clear. We use our usual importing of our packages. We're gonna define our butler, the usual butler for the DP0.2 simulations that we use. Then we find our plotting parameters. An important parameter is a parameter that is colorblind friendly. It is a palette that we can use from Matplotlib. And then as many of our notebooks, we start by defining some utility functions that we're going to use later. So we have this conversion between the standard deviation of a Gaussian function and the full width of half maximum. This is a standard result that we have here. And just giving a little bit of foreshadowing that this is the kind of things that we're going to use later. So we define a two-dimensional Gaussian profile here. And then we're going to have function, it's a helper function that is going to receive a PSF model and is going to give a point in which we want to evaluate that PSF model. And it's going to just, it's a wrapper because it's going to look into that PSF model here and it's going to tell us, it's going to get functions that helps us do things like computing the shape of the PSF model at a particular point, getting the size of this, what is called this determinant radius, or computing an aperture flux, computing the peak and computing images or the dimensions at a particular point. And this function is just meant as an example of how you can, all these objects carry information that we can use. So your model will come also hopefully to keep poking into those objects and see what else you can use. There's another function that has calculates an azimuthally average radial profile of the PSF. So I'm not going to go a lot in the details into that. It receives an input at exposure, and then we calculates that, and then it also actually does a Gaussian fit, and then we calculate the profile and does a Gaussian fit profile and gives us some information about that based on that fit. And another helper function is one that is going to calculate the encircled energy or what is called the plot, the curve of growth of the profile. And we're going to see later what we mean exactly by this. And then we have another helper function to calculate the two-dimensional contours. So yes, okay. Okay, moving on. So we're going to start with exploring the PSF from a single epoch image or a CALEPS image. And then we're going to do a comparison with what we get from the coordinate images. So for getting this CALEPS image, we're going to need information of a visit and a particular detector. So we use that from one of the previous notebooks in DP0.2, tutorial 3A. We take a look at it, just see what the scene looks like. And then it looks like this. And then the same CalEPS object is going to have the information that we're going to use for the PSF. So we're going to get some information. There is like a general information. You can explore all the options that this information function gives you. But one of those is the PSF model that we're going to call here the PSF CalEPS. So I'm not going to go a lot into that right now, but we're going to start exploring what that PSF model is actually giving us. So we pick a point. I just picked a point in this image at coordinate 2000 and 3500. There is a subtlety that it needs to be converted into a geometric point that the LSST science pipelines objects are going to understand. It's called a point 2D. So we just define a tuple here, and then we just convert it to that particular type. And then we start using this PSF model in order to calculate the properties that we want. So here we just compute call this function compute shape that is calculating the second moments. So we have the second moments in xx, xy, and the cross component of the second moments. And this we can do linear combinations of these quantities to get ellipticities or sizes, for example. We also have helper functions that already do that for us in the PSF model. So, for example, if we want to obtain the sigma of the PSF model, or this what is called determinant radius here, we just call that function that is calculating that using the second moments. And we displayed it here. And here we just displayed it in different units. We can calculate them. Well, the units are the same in different definitions of size. One for sigma and one for the full width of maximum using the constant. So here we're doing basic operations. We're just kind of exploring the kind of things that we can do. We can compute an aperture flux at different sigma and the same position. And then just for illustration purposes, we can see how it behaves as expected, at least increasing monotonically speaking. We can also get the peak of the PSF. So this object again has all those functions. But then, as I mentioned before, then one of these functions, one of the helper functions that we wrote is already doing that for us. So here I call that function that I defined earlier, that is just basically doing everything together and gives us just some statistics of what we can see of this PSF. But then we can do this at any other location of the image, and then you can see the subtle differences between two different points of this single epoch PSF. Then we have two ways of calculating an image or displaying the PSF. They have names that might not be that intuitive, but one method is called compute kernel image, and the other method is compute image. And just they basically do the same. They give us an image of the PSF, and the only difference is where the PSF is going to be centered. So for one method, the compute kernel image, it centers the PSF at a location called 0, 0, at a 0, 0 location, as you can see here. Before doing the displaying so we have the same PSF model object here that we've been using, and then it has the helper function in the particular point. We need to do a conversion to something that we can plot using matplotlib. But then it gives us an image of this particular PSF. For this particular simulation, for this particular exposure time, it gives us something that looks nice and symmetrical. But then we just compare it with the other function. We can do exactly the same thing. And this other function gives us the position, the image, it locates the PSF, but in the coordinates of the image that are like of the actual point. So it's not centered at 0, 0 like the other one. And in order to do that, it needs the information of the astrometric solution, which is the mapping between the pixels and sky coordinates. So that object needs that information of that astrometric solution. And then in the same way that the PSF model was available through in the CalEP, so this info CalEPs, we got it from the CalEP, so that info CalEPs object gave us the PSF model is also going to give us the WCS model as well, the WCS function or the astrometric solution. So we just needed to do that extra step there, do something similar to convert here in order to be able to visualize it. And we have a similar image, is just located in different points. Okay, moving on. Then I'm gonna leave about 5 minutes for questions at the end. So, but I'm almost done with this because okay, so we have the option of course, so we can download these images if you want. So this is just an example of how you can save image in your home area. And in this case, it's saved as a fit image, which you can download and look at it with DS9 or whatever. I usually just use notebooks, but yeah, so there is that option to save it there. Then, so in this section, we're basically doing the same, but now with co-added images. So this is, there are subtleties, and actually it's not trivial. The way in which, for example, is done in another precursor survey called the Hypersupreme Camera Survey, which actually uses the LSST science pipelines or other versions of the science pipelines, is you can have the model of the PSF at every single epoch image that is going to go into a particular coordinate, and then you can do a certain resampling and using certain waves to combine that PSF into the PSF of the co-added image. So you're going to have a PSF model of your co-added image. However, it's not that trivial, and there's in the second notebook, I'm going to refer a paper in the literature in which some of our colleagues in the dark energy science collaboration of the LSST have written a note detailing how the process of coaddition of the PSF model in something like this is kind of ill-defined a little bit, and you need to pay a little bit more of attention. But for the purposes of what we have here, we're just basically repeating more or less what we did here, but with co-added images. Yeah, so okay, so we're gonna retrieve first the right ascension and the declination coordinates of the same point that we used previously. So we're gonna use our astrometric solution that has a handy helper function that is gonna give us the transformation from pixels to sky coordinates. Then you need to keep in mind that I think this is giving us radians. That's what these two functions are actually giving us here. So you're going to retrieve the coordinates in the sky, but in radians. So it's actually better to convert them to degrees. And this is what we're doing right here. Then we're going to select a band, a particular band. And one exercise is nice to change bands and see how things change, and define a point, a spherical point in the sky. And for that, we need to use this sky map. Then we need to see how, in which track, and remember that we have the DC2 simulations in the sky is divided in patches, and it's divided in tracks. So we need to find the exact track patch and also the band information so we needed to do all these preparations to find this preparation in order to be able to tell the bottler which coad to get. Remember that the bottler is like a bottler and is retrieving what you ask it to, but you need to be able to tell it the minimum information in order to retrieve what it needs. So maybe speeding up things a little bit because I also want to go through the other notebook. Okay, so we got the coad. We did the image of the coad. We see more objects. It's as expected. It's a coadded image. We do something very analogous to what we did before, in which we get the information from the same coad. We get the PSF model from that information object that the coad is giving us. And then again, I'm gonna go not gonna go a lot into this example. There's a note here about the size of the PSF in the coad with respect to the individual calibs. In this case, so we're doing the same. We're calculating the properties with the helper function that we have. And the note here is just telling us that you can see that the coad here is a little bit farther than in the individual image, because we just happened to pick an individual image that was below average. The coad is giving us the information of the average image quality, just giving that point. But here we're using the same images that we used before, the same methods for displacing that we used before. One of them gives us the image centered at 0, 0, and the other one gives us the image centered in the coordinates, in the particular coordinates of the image that we selected. Just to finalize and have some time for questions, then we're just using the function that we defined at the top in order to do this type of basic analysis, or what we call first order analysis or rapid analysis of the PSF. And actually some of this code is used in the auxiliary telescope right now. Like people need this type of rapid analysis in order to determine how things are going, and the oxtel that it's going to be helpful for calibration purposes for the Rubin Observatory. But right now it's serving a lot as a pathfinder in order to test all our code and to integrate all our systems. So this code to plot this is based on a code written by Merlin Fisher-Levine, and I decided I thought it was nice to use it to here in these simulations. So we have the profile, the average profile. It does a Gaussian fit. It gives us some properties, including skewness, for example. You can put whatever you want here. We have the two-dimensional contours. You can see how you squint a little bit, you can see how the deep coat is a little bit farther than this one. And of course, here in the simulation, things are maybe nicely and well behaved, right? But you can imagine how with actual data, things can be like be noisier or not in one case or the other. Then this is the curve of growth that I was talking about. It's a cumulative measurement of the cyclic flux, energy. And that's it. That's what I wanted to show. Like there are some exercises. I think one of them tells the user, for example, to plot these profiles in the same panel, which I did here, just for ease of comparison. You can see the coat and the individual profile and how they change a little bit. Okay, so that's we have a few. That's it. That we have a few minutes for questions or comments so far, and take a pause before I move on to the other notebook. And yeah, so this was meant to illustrate how these objects have all these functions that you can poke and how carry all the information and the differences between single epochs and coated images. Let me see, do we have anybody in the chat? No? If not, it's okay, we have a few minutes.
Nothing in the chat.
Okay, thank you. Okay, no problem. We can maybe move on to the other notebook that shows us an example of analyzing the PSF in the context of cosmology and weak lensing. And I chose this because my background is in weak lensing, and I wrote my thesis on studying systematics for weak lensing with the dark energy survey some time ago. So I thought it was interesting because as you may have been seeing in the news, a lot of the projects like the dark energy survey, the hyper supreme camera survey, hyper supreme cam survey, kilo degree survey, there's a lot of these weak lensing projects that are giving us constraints of the parameter of the equation of state of dark energy. And these are very, of course, they are very complex analysis, but a lot of these papers, they rely on the systematics control. And then usually you find a companion paper that shows us, how do I know that I can trust your PSF model in order, when you're giving me this gravitational lensing signal that tells us about dark energy. So a lot of these tests and systematic null tests is done in these companions papers that do. I'm going to show some of the metrics that are used in order to say, okay, this PSF model is good enough for the science that we want to do with this particular survey. And then there is the question of, are these models going to be good enough for the LSST year 1, 5, and 10. And then, of course, it snaps in the middle of the demo. Let's see what happens. Okay. Did it run or not? Let's see. Just 1 second. Oh, still there. Okay, so what are we gonna see here? We're gonna now we're gonna get the properties. We're gonna look at the catalogs that are associated to the simulation. So we have an object catalog and a source catalog. Object catalog from coated images and source catalogs from single epoch images. We're gonna see the kind of properties that then are gonna help us calculate properties that can tell us more about the quality of the PSF model. And then we're gonna see some examples of or properties of the PSF. For example, the wavelength dependence of scene, and then something that is called the raw statistics that is very used in weak lensing, and we'll see what that's about. And then this notebook again was developed in collaboration with a lot of my colleagues from the community science team, but as well many of the sections were taken from members of some of the science collaborations and also other Rubin members, and then they were adapted to here. So I wanted to acknowledge my colleagues. So as I was, the introduction tells us a little bit about weak lensing, why this is important. And then this is bias for the static science that I do, but of course the PSF modeling is also very important in our time domain science and other aspects, of course, of what the LSST is going to do. I already explained what the sections are going to do, but here I also wanted to point out that there are some examples to the literature. There is a recent review on PSF modeling, some references to different chromatic effects that have to do with the PSF, and chromatic effects is that things are going to be different with wavelengths, and that's going to complicate things, and there are multiple effects, and each one has a different wavelength dependence. And then if you want to learn a little bit more about the raw statistics, and the PIF modeling software that I mentioned before, you should look at this paper by Mike Jarvis, all from the Dark Energy Science collaboration, that tells us about PIF, and then also look at the other papers by the HyperSupreme survey. And this is the paper that I was mentioning about co-adding PSFs and how it should be. This paper actually does a good job in constructing a mathematically well-defined co-added PSF. So by Rachel Mandelbaum and collaborators. Okay, so we start importing the usual stuff that we need. We're gonna do some fits. We import something that is called tree core. So that's another important piece of software that is gonna help us calculate correlation functions in general. So this was a package developed by Mike Jarvis at the University of Pennsylvania. And it does calculation of correlation functions that are gonna be very important for PSF quality assurance and for science, for weak lensing. And this is a code that calculates 2-point correlation functions in scalar fields, vector fields, spin 2 fields, which is the shear field, etc. And it also calculates 3-point correlation functions and stuff like that. But I wanted to mention this code because it's going to be used. It is already being used in the cosmological analysis for DES, HSC, and our colleagues in the Dark Energy Science collaboration, the LSST, are basing a lot of their analysis in this code. So there's tree core. There's a Python interface, you can import it, but then this is the links to documentation. So we start by defining the usual helper functions. As I mentioned, we're gonna deal with the catalog. So we're gonna get the table access protocol service, the TAP service for DP 0.2. We defined our colorblind friendly palette. And then just we're gonna do a fit to a power law here. So later, so it's defined there. The first thing we're gonna do is to get the PSF properties from the objects and sources catalogs. Objects again from deep co-added objects, and sources for single epoch or CalEPS objects. So one way of doing it is like, how do you know? Like, oh, how do I know? You can go to the schema browser. I know many of you have seen this schema. It has a lot of columns, but it's all here, and you can take a look at what says PSF. That's one way of looking at it. You can also do a query here, which I'm not gonna do, but it's an example. It's a little bit more systematic example of doing a query of the catalog object and then looking for the columns that have the PSF. So in particular, so if we look at the object catalog, we're going to be interested in a particular band, which here I define actually I might have defined. I haven't defined it yet, but it's defined here below. I'm gonna, and I mentioned this, I mentioned this band, because one nice exercise is to rerun this notebook, or maybe you can do your own loop in different bands and see how things change. But coming back to this, we have the object catalog. We're gonna get the flux. They're gonna get the flux error of the PSF model. This flux is getting by PSF, by least square fit of the PSF model. We're going to get a flag that is going to tell us if the PSF model converge or not. We're going to get we're also interested in these second moments that are going to help us calculate sizes, for example, as a linear combination of these, or ellipticities. These are the second moments of the surface brightness. We also have another flag that is going to tell us if that star is from that catalog was used to do the PSF model. So I mentioned that we use bright stars usually to do PSF modeling, but we don't. So first we start doing like a galaxy star separation with a size magnitude diagram, for example, and something more complicated. Then you have your set of candidate stars. But even between that, we usually separate like 20% or so of those stars to have it as a testing set. This is something that is a standard. And then you use 80% or the remaining 80% to do the actual modeling of the PSF. And then you can test your model on the reserve set of stars. So I think this flag is telling us if the PSF was using that modeling or not. And there are other flags that are telling us if the particular, so we want to calculate the PSF at a particular point, let's say like in a galaxy. And then that's telling us like, oh, but maybe the PSF associated to that point is not that exact because we're close to an edge. So I mentioned one challenge, which was coating the PSF from single epochs to coated image, so to produce that coated PSF model. There are, of course, other challenges in practice that there are discontinuities in the boundaries of the detectors, or the conditions from one single epoch to another epoch are going to be different. So I think this particular flag is telling us if the objects were close to a point in a PSF that was close to the edge. So they're telling you maybe don't trust that much that PSF, but there's the option, and then you can filter for that. Okay, so moving to the queries, this is moving ahead. We pick a field. I think that is the same field that we used in the previous notebook in a particular band. And then the query is going to retrieve some of the quantities that I already described. And we have other flags that are other criteria that were also used in other notebooks. We want things, for example, to be bright. We want to be within 2 radius, a 2-degree radius of the center point. Something that it has to do with the blender, if it's in order to avoid duplicates and unblended objects. And then again, there are some other flags that gives us quality of the PSF model. Then you might see other quantities here that are not fully explained here, but those are quantities that are later needed to calculate these 2 correlation function statistics that I will mention in the last section number 5. So we do our query, we get our stuff with our filters. Hopefully this will give us a nice sample. Then this table, the results table, we're going to call it the object. We calculate the size of the PSF using the second moments just for convenience, and we add it to the table. So for each of the bands, we calculate different PSFs, the PSF size. And then we do something similar, but for the sources. So in this case, we also save our result, but here in another table called sources. So now we have the objects and the sources. We calculate the size and we put it in the table just for convenience. And then we move on to the other sections that are just going to help us visualize what this PSF model has. So I mentioned the 2-point correlation functions, how that's important in PSF modeling. In cosmology, historically, it was introduced by Jim Pebbles many years ago, and basically it tells us it is used in cosmology because one of the questions is like, is the large-scale structure of the universe uniform or not? So we wanna the 2-point correlation function it gives us a measurement of the probability of finding an excess or not over a uniform distribution of a particular galaxy. So this is part of the historical reason why this is used. And the current cosmological analysis based on wavelengths, it do something that is called like a 3 times 2 point analysis. I'm not going to go a lot into the details of that, but correlation functions are important, and that's why we are looking at this. So here we're going to use tree-core to calculate the correlation function of the PSF modeling, or the PSF model for the objects. So we need to define some of the parameters that tree-core are going to use. So we imported tree-core, and then in order to call tree-core, you need to pass it the catalog that you're going to use. So you pass the coordinates, then you pass this K is actually the field or whatever you're going to calculate the correlation function of, which in this case is going to be a size 2-point correlation function, the size of the PSF. And then we remove the mean size. So we actually have like a sort of normalized field, but it's just basically passing the size of the PSF. Then these are some options from tree-core. You pass the units, and then there are some other correlation functions about the binning and the steps, and that you can find more details about that in the documentation. Then we initialize the object that is going to give us the correlation function of this scalar field. And then you pass the configuration that we just defined, and this process is calculating the correlation function. And it actually doesn't take that long. Then it gives us, it calculates the correlation function in an object that is called C, is the Greek letter C, or however it is pronounced. But that's how we retrieve this, the actual calculation, the results, and then we retrieve the beans. So then here we just plot it. We just create here our nice plot. And then here for the objects, we can see the variation of the PSF model in this particular field of view for this particular band, and then how the correlation function as a function of separation decreases, and then until it starts getting closer to the characteristic scale of this area that we chose, which is about 3 degrees or something like that. Well, so that's just an example illustrating that. We're going to do something similar with the sources. In particular, well, we see how here in the case of individual images, we would expect that for the coat, many of the correlations get kind of averaged down. For individual sources, we can see a gradient that it's likely due to atmospheric turbulence, or what is called the Kolmogorov atmospheric turbulence. And then things actually decrease lower. It's not, the correlation doesn't decrease as rapidly as with the coat. So things are more similar to each other because there are more correlations in shorter spatial scales. And this is just an example. Again, it's a simulation, but it's something nice that you can do. And this is the kind of survey property maps that you want to start doing when you have the actual survey with different epochs and different bands, and see how things are correlated or not in different parts of the sky. So in this case, we have one band, which is the I band. So far this is not showcasing contributions to the variation of the PSF due to being in different bands, or the wavelength dependence of these changes. So in section 4 is going to illustrate one of these effects, which is the wavelength dependence of scene, or the characteristic size of the PSF. So this introduction just basically is telling us that this wavelength dependence of scene, it should follow this functional form from Kolmogorov turbulence theory. You can arrive at this result that the scene, or the size of the PSF, should go as the wavelength of the PSF to the minus 0.2 or minus 1 divided by 5. So that's what the Kolmogorov theory tells us. As I was mentioning before, this is just one contribution to the variation of the PSF with wavelength, the scene. It is an important contribution, but there are other contributions. One of them is called what is called the differential chromatic refraction. Actually, my first paper was related to the impact of this DCR and weak lensing. But then there is this differential chromatic refraction. You can find diffraction due to the telescope. Then even within the CCD, we're gonna have variations in the silicon. That we have CCDs that are 100 micron thick. And then we have a fast beam of the LSST because of the design. If we want to do a fast survey, fast, wide, and deep, remember. Anyhow, the point is that it's a fast telescope, it's converging at a very high angle, and then with the thickness of the CCD, you're going to have different effects depending on the wavelengths of the incident light. And then there are here papers that tells us more into detail about how these effects can introduce biases in observables of interest as the basic observables that we usually care about, like photometry, astrometry, measurements of the galaxy shapes and size, and also higher order moments. So usually shape and galaxy and shape the like first and second order moments, but you can also keep going and see how this affects higher order moments of the intensity. Okay, well, this is just the background. And the way we're going to do it here is we're going to just calculate the mean size of in each band, the mean size of the PSF in each band. And in each band, we're just going to use the midpoint of the field because we get them from the LSST science book. And basically, we're going to do a fit using SciPy. So nothing fantastic going on here. It's actually very basic, but then we use optimize curve fit. It's going to give us the parameters. It's going to give us a covariance matrix associated to the error of those parameters. We can just take the diagonal of the square root of the diagonal of that covariance matrix to give an estimate of the parameters of the error of the parameters. And then we just do the fit of the wavelength we just fit the wavelength as a function of the size as a function of wavelength. Something very interesting, and then maybe this is an exercise for the learner, or maybe a ticket for myself, is that when I was preparing this notebook, I was happy because, oh yeah, it gave me something very close to the expected from Kolmogorov theory, and this is what I wrote. This is very close, 0.196 within an error bar that should be close to minus 0.2. And the person who originally wrote this piece of code, I think Tianqing Zhang, he also obtained a similar result. Now, when I was rerunning the notebook, I obtained an exponent of 0.169. So that's something interesting that should be interesting to be checked, and maybe the code is always changing, so it's not that surprising, but something to keep in mind. But for illustration purposes or pedagogical purposes, basically we were just calculating how the size changes as a function. We can see as a function of wavelength, and we can see a clearly dependence on that. We can see the fit. We can do a chi by eye, and then it's like, oh yeah, I guess we could do better. So that's something interesting to do. Okay, then the next cell is just giving us the same plot, but we're visualizing the histograms of the sizes as well, and then reminding us that we took the mean of those histograms. So maybe we should be taking a different, maybe the median. I don't know. There are things to look at, or maybe look at the outliers and see what's happening there. But this is just another way of visualizing the result that we just obtained. So this was to illustrate one effect of the PSF, one chromatic effect of the PSF, which is the dependence on the scene on wavelength. Then to finalize this, I wanted to calculate this raw statistics. This raw is the Greek letter rho, and it's actually, I guess it's a play of words as well, because the person who wrote the paper, their name is Rowe, R-O-W-E, Barney Rowe. So that's Rowe et al. 2010 or something like that. But we're going to basically calculate these correlation functions. We could directly use 3-core, But another thing that I wanted to illustrate here is the use of this package called analysis tools, lsst.analysis.tools, which is a package designed to generate quality assurance plots and metrics for the outputs of the LSST science pipelines. And we as developers of the LSST science pipelines and many you as users, as delegates, have seen this in maybe boot camps, and this is a package that we want to keep using more and more. So effectively for this exercise, this the analysis tools is doing a wrapper of 3 core, and it's calculating the raw statistics for us. So again, you can calculate this directly with 3 core, calling 3 core, or in this case, just as an illustration of analysis tools, is gonna do it for us. Well, and then the analysis tool, so it's divided into something called actions. That is the thing that is going to calculate our metric, in this case, the raw statistics. And there are different stages. In the same way that before we were, for 3 core, we were preparing the configuration. Here we do a preparation stage, to some filtering of the data. Then something to modify the data, something called process here, and then actually it's something that runs the code and runs the metrics. So we have this produce stage. So this is just basically telling us what's going to happen in the next cells. We do some filtering. I guess we select start with high signal to noise ratio of 20. Then we do some changing of the parameters of 3 core. You see here we're accessing 3 core via analysis tools, basically changing the configuration parameters. And then when we think we're happy with our configurations, we tell it to actually do the calculations. So as I was mentioning before, when we did the query at the beginning, we were not using certain fields because we're holding them in order to use them here. And the way I determined this was looking at the documentation, and it was a lot of trial and error as well. When I was running things and it kept telling me, oh, I need this and I need that. I was like, okay, let's see. And then I looked at the documentation, it's like, okay, it makes more sense. But then these are the fields. If you want to know about the schema that the columns that the analysis tool is going to need in order to calculate the raw statistics, then we have this cell here that is telling us the quantities that we actually need. And then again, we're doing this in the I band. Then we're calculating, actually here, we're actually calculating the result. Then it gives us some logs here. We can take a look about the results. So the processed results is the object that is going to have the results. We can access them as the mean radius, this psi, C, remember, so I call it C there. This is called CP because it's called C plus. It has to do with the fact that the lensing signal can be divided into an E mode and a V mode, and this is a similar theory to what you have in CMB modes or in electromagnetism. But the bottom line here is that this C plus is the actual signal that you're after, but weak lensing should not produce a C minus signal because of reasons, of symmetry of weak lensing. I don't want to go a lot into that, but the point is that you could also access that other psi minus correlation function and check that it's consistent with 0, and if not, it's because you have some systematics in there. I just wanted to mention that out. Here I'm just printing these objects, whatever we got from the results, but then it'd be nice if we can just plot them. So we finally arrived to the famous raw statistics. And what are they? I've been saying that they're 2-point correlation functions, and they are two-point correlation functions of what? Of the residuals of your PSF model. Which residuals? You see these deltas here, delta E. Usually you calculate, you have your set of stars, and then you calculate your model based on that set of stars. You can measure the ellipticity on your observed stars, and you can also get the ellipticity that your model tells you that your observed star has. And then you can calculate the residual of that, and that's what this delta E is. And then this, the way in which the theory is developed you can propagate, you can get the requirements for a survey like DES or LSST for systematics of how much systematics you can tolerate for a weak lensing analysis. Then you can propagate those errors into these rough statistics. And then you can get, usually in the papers, they show you like a band of error that is tolerated, that is more, I think it's more or less what is shown here. I believe this is the requirement. I think maybe this is just an arbitrary threshold in this case, but it's of the order of that magnitude that the tolerance for LSST year 1 or year 10 is. So if you look at the papers on DES, you look at the raw statistics, that is the raw statistics, and then demonstrating how these tests, these statistics that should be small, are within this band of tolerating error. So this is one of the statistics. There's 5 or 6 of them. Again, calculating different types of correlation functions between the residuals of the ellipticity, the residual of the ellipticity, and the ellipticity of the PSF itself. Then we do linear combinations with the fractional residual of the size. So we do a delta T, which is T is what we were calling the size of the PSF, and it's fractional because you divide by the size. And these are the different types of correlation functions here that we have, which for the raw statistics, which in this case, they're kind of small. This is like a simulation that is more or less well behaved. And we also have like a small, relatively small patch. Remember, in weak lensing, we want to have as much area as we want. And that's one of the drivers of the LSST, wide and deep. That's good. For weak lensing. So in this case, yeah, we have like a smallish patch of the sky, a nice simulation. So maybe we shouldn't read that much into like, why are these too small? But it's illustrating how we calculate this type of raw statistics. Then some exercises is maybe changing the band, or using calculating the PSA ellipticity. For example, we calculated the size based on the second moments, but if you do a different linear combination of the second moments, you can get an ellipticity. And then there are other exercises here that tell us how to maybe change the band, as I was saying, how that things we're going to change in different bands. And I think my time is up. Sorry, I wanted to leave some time for questions. So thank you. Yeah, I see that Lian in the chat wrote raw statistics, which is what I was trying to say. Yeah. ROWE, the last name of the person who wrote the paper, but they're denoted by a Greek letter rho. And in my Colombian accent, it sounds the same. Rho. Maybe in English, it sounds the same. Okay, sorry that we ran out of time, but we still have a few minutes if somebody wants to comment something. I'm always happy to answer, to follow up on community or on any of the other channels. That you can always send me an email as well. And Lian is telling me that they sound the same in English too. Perfect. Yeah, it's a play of words. Anyhow. It's not my accent. Okay, it's okay. I love my accent. But yeah. Okay, do we have any questions or any comments? We have 1 minute. Sorry, I got excited, and we had a lot of material to cover. Again, any follow-up question, please feel free to send me an email. Use community. I want to encourage people to use community, because if you have a question, then it's likely that other people have that question. But I don't see any, let me see, any hands up. If not, then thank you so much. I mean, this was fun. I thought it was fun for you as well. And I hope to see you in the next assembly.
Thank you, Andres. That was very helpful.
Thank you.
Thank you.